So last time we talked about how the geniculate it receives input from the retina and what that map looks like. So we talked about these conformal maps. That was a map that preserves local shape but not size. And this was relevant to the fact that anytime you look at something and it gets in your center of gaze, it gets hugely big. And so somehow the rest of your brain is getting this insane movie where every time you look at something it blows up, and yet your internal experience is, yeah, nothing's changing size, everything's pretty much in the same place. But that's constructed, the thing that's actually coming into your lateral geniculate and V1 is very, very, very different looking. It's this strange movie that you would never recognize if you actually could see it playing out on your V1. So what we're going to talk about today is going from the geniculate up to the cortex. And I'll break it into two chunks. So the first chunk is, let's look at the visual maps that go to V1 and V2 because those are different. V2 is almost a more typical visual map in the brain, but it's strangely different than V1. And then I'll talk about all the other maps. So I'm Mr. Map, so I've mapped all different kinds of visual areas. We're primates. Primates live in the daytime, have a big emphasis on vision. Almost somewhere close to half the cortex in a macaque monkey consists of visual areas. It's not quite as much in humans, but pretty close. And so let's talk about all the other ones. So there's like about 30, 40, 50, depending on how you subdivide. So that will be other maps. So before we get started, if you read any of the literature, most of the data on the actual connections of visual maps comes from animals where people have done invasive experiments. And in particular, it comes from a lot of data from macaque monkeys. And so it's worthwhile just sort of drawing out a picture of a macaque monkey and where the various sulci are in a macaque monkey and a human monkey to sort of be able to transition back and forth between them. So this guy is a macaque monkey, commonly used monkey, an Asian or African monkey. And so what are the major sulci here? So there's one here called the lateral sulcus, or the Sylvian sulcus, you've probably heard of that. And then there's the central sulcus. I'll label them in a second. And then there's the intraparietal sulcus, kind of looks a little bit like that. Then there's the superior temporal sulcus. And then there's another one here called the lunate sulcus, probably haven't heard of that one. And then there's the inferior occipital sulcus. And then there's the principal sulcus and the arcuate sulcus. Okay, so there's our major sulci. So let's label them all. So we've got this guy is the principal sulcus. And this guy is the arcuate because it's kind of arcuate. This guy is the central. That's an easy one. And then we have the lateral sulcus or the Sylvian sulcus. That's this guy. This one is the superior temporal sulcus. And this guy is the lunate sulcus. That's like, you probably haven't heard of that one. And then this is the inferior occipital sulcus. And then last but not least, the intraparietal, IPS, intraparietal. So those are the main sort of folds in the macaque brain. And most of those are there in the human brain, but it's a little, color should I use? Let me just make the overall contour here a slightly different color. Okay, so here's the human brain. Human brain is even bigger than this, but I'll just leave it at this. So here's our big human brain. So we've got the same lateral sulcus. So here's our lateral sulcus. That guy is lateral, or the sylvian. And then we've got the central sulcus. Central sulcus is pretty much there. Now, when we get back to the intraparietal sulcus, what happens is it's typically sort of broken up into a post-central sulcus, and then there's kind of a separate intraparietal sulcus. So this guy is post-central, but you can sort of think of post-central as basically just the front part of the monkey intraparietal. And then this one is it's got strange names, but usually it will be called intraparietal, parietal. And there's kind of like this strange history of the lunate sulcus. There was this sort of racist idea that only certain people had a lunate sulcus, and so it kind of had a cloud over it. But the actual lunate sulcus is still there, and it's slightly bent backwards, and it's called the transverse occipital sulcus. So transverse occipital sulcus, and that basically equals the lunate. So this is just to help if you ever go back and forth with the actual sort of monkey data. And then there's the STS, but the STS usually, instead of just sort of heading up toward the intraparietal. Let's pull that intraparietal in a little bit like that. Okay, there we go, much better. It tends to sort of break up into, sometimes it goes up, sometimes it goes down, sometimes it sort of goes up and down. It's a little more variable. And then when you go to the frontal cortex, you mainly see two sulci, like the superior and the inferior, frontal sulcus. And what are those? How should we think of those? One way of thinking of those is that if you take the principal sulcus and the top part of the arcuate sulcus, that kind of basically forms the more dorsal, the more superior sulcus in humans. And then the one under it is kind of, you can think of that as more or less equivalent in terms of what areas are there to the bottom half of the arcuate. So here's our superior frontal, inferior frontal. Here's the STS. That guy was and then there's another sulcus. There's another sulcus down here, which is like the inferior occipital. So that's the inferior occipital. Okay, and central. Now, when we compare between these two animals, what's the overwhelmingly biggest difference between a macaque monkey and a human? And what that is body size. It turns out that the most important, by far, the most important factor affecting brain size is body size. This explains something like over 90% of the variance in brain size has to do with body size. And most people think, well, body size, what what's that? But if you look across an animal that weighs just like 10 grams up to like an elephant, what you see is that body size overwhelmingly determines the size of the brain. So body size is by far the most important thing. So, you make a bigger body, you get a bigger brain. Now, do you need a bigger brain? Not clear. So if you look at a small rodent, like a little white-footed mouse, got a little teeny tiny brain, you look at something like a capybara, it's a 150-pound guinea pig, good at swimming, can hold its breath underwater. It has a hugely bigger brain. It's like 30 times bigger than the small rodent. Is it sort of 30 times smarter? Well, it's kind of, it's like a really big guinea pig. It's got a much bigger brain. But one thing that's interesting when we compare animals of different body size, what we find is that as you blow up the brain and as you blow up the body, the brain blows up in addition. But surprisingly, you might think, well, if you've got a bigger body, you probably need a bigger somatosensory cortex because there's more skin to service, or to sort of like, deal with information from. But interestingly, it turns out it's not that way. It's exactly the reverse. So what happens is as the body increases in size, the brain increases in size, but the amount of primary sensory cortex as a proportion of the total cortex gets less and less for the bigger brain. So if you look at a small rodent, it has a larger percentage of its brain is primary sensory cortex. If you look at a capybara, a smaller percentage of its brain is sensory cortex. And so there's a scaling rule which says that as you increase the body size, the brain size increases, and non-primary areas also increase. And that's true of humans, of course, as well. So we have more non-primary cortex than a monkey does with a smaller body. Does that mean we're smarter? Well, yes, not necessarily, because you can see exactly the same thing happening if you compare a small rodent to a large rodent. The large rodent has a lot more non-primary cortex. Okay, so what does that mean in terms of like how the areas are arranged? Well, we know some primary somatosensory cortex is over here. Primary auditory cortex is kind of stuck into the lateral sulcus. Primary visual cortex is over here. So what that's going to mean is that when we compare a macaque monkey to a human primate. So when you compare these, we're going to expect to get more space in between. But what's that going to do to the general sort of location of areas? Well, what's going to happen is, so here's our primary somatosensory cortex in a human. The primary visual cortex it's almost barely visible because most of it sort of like has been shoved around the back. So here's this is V1 here. So if you look at a macaque monkey, you can see a whole bunch of V1. So you can see V1 on the lateral surface. And so the auditory areas are more or less where you'd expect them to be, stuck in here. But what's happened is that essentially everything is kind of sort of pushed around the edge. So areas sort of go that way, and they go that way, and they go that way, sort of around underneath, and they kind of like, head out this way, and they head out this way. And so when you try to sort of compare humans and macaque visual areas, what's going to confuse you is that a lot of the areas are just kind of like pushed around the edge. And what is that? Well, there's some extra non-primary cortex, which is bigger than the equivalent area in a macaque monkey, mainly because we have a bigger physical body, and so therefore a bigger brain. Okay, so that's just that's like the intro to sort of like where some of these areas have gone. So I mean, we'll just take one example. Like there's an area called LIP. lateral interparietal cortex. And that area is sitting in the interparietal sulcus. It's right about here. So that's interparietal. This guy is LIP. And so where is LIP in a human? Well, people went looking for it, and they said, yeah, it must be like around here, somewhere in the interparietal sulcus. But instead, where is it in a human? It's way on the edge over here. And how did it get there? That's the human LIP. It got there, because everything kind of stretched around. It sort of goes over the top, it goes around the back, it goes underneath, sort of goes around onto the midline. So it's a little mind-boggling when you try to sort of look at one animal and another animal. Everything's slightly in a different place, trying to figure out where stuff is. So that's kind of an intro to that. Okay, so now let's talk about visual maps in V1 and V2. And so if we do that, there's always going to be a problem on the test about the visual maps. So down at the bottom here, we're going to draw the visual field, looking out at the visual field. So here's a vertical line looking out at the visual field. I'll draw the whole visual field. And then here's the whole visual field. And then here's a horizontal line. That's the thick dashes. And star is right at the center of gaze. Okay, there's our horizontal line. And here's the upper field and the lower field, the upper field and the lower field. And so this is the left hemifield, meaning left visual hemifield, looking out. So that's looking out at the world. And this is the right visual hemifield. Now, the first thing we know is that the way these maps work is that the left visual hemifield, the left world, goes to the right brain, and vice versa. So now we have to decide, should we draw the right or left brain? So because we really need to draw both the left and the right hemisphere to represent the whole visual field. But let's just draw one. And so if we draw one, let's draw the left hemisphere. So here's the left hemisphere. So this guy is the left hemisphere. So the left hemisphere is mainly going to see the right side of the world. And so to start off with, let's just cross out this side, okay, because the right visual field is going to be the main thing. So this is the right visual field, is the main thing that goes to the left hemisphere. The left hemisphere, right visual, and that just goes back to the very beginning where we said the right world goes to the left brain, and the left world goes to the right brain. Okay, so now what does the actual map in V1 look like on the cortex? So let's draw that map using these same symbols. So I'm going to pull it so that the actual center of gaze is just right here at the very edge of the brain. I'm going to pull it a little bit forward so that I can make it look slightly more like a macaque, so that we can sort of see what's going on a little easier. So what it looks like is the vertical line is right there. Remember, this is just a half of the hemifield. And then here's the horizontal line. But it goes around the back. So if I kind of flip the cortex around like this, here. So here's the corpus callosum. So if I flip it around, we can see that this continues, onto the back of the cortex, and similarly, the vertical meridian continues onto the back, and then here's the periphery. So that's V1. That's what V1 looks like. In humans, there's more of it around the back than there is around the front. In macaques, there's more of it around the front than there is around the back, around the midline. So that's what the visual map looks like. And then you probably know that the visual map is upside down, and so the upper field is sort of lower than the lower field. So the minus, which corresponds to this over here, so it's flipped. And if we look at that, so let me just label this guy. So this is V1. Is that getting in the way of something? Yeah, I can move that slightly out of the way. Yeah, okay. So this guy is V1, and so this guy is V1 plus. That's V1 minus. And here's more V1 minus on the midline and more V1 plus on the midline. So this is midline view. And this guy is lateral view. Okay, so that's V1. Now let's look at V1 relative to the visual field. So here's our visual field, our right visual field. So here's our right visual field. And let's just take this visual field here and sort of like paste it on top of the cortex. So I just drag this guy from the right visual field and put him up there. And you can immediately see that what you have is a mirror image of the visual field. Because if I take that plus, the plus goes over a minus here, V1 minus. So, and now I could take that guy, I could put it up there and rotate it around like this, but then that would make the lower part up here. But then again, you'd see it's still a mirror image. The only way that you could completely line it up would be to take this guy, rotate him around over here, and then flip it over. And so the movie that plays out on your V1 is a mirror image of the world. Is that particularly functionally important? Not particularly functionally important, but if you could put a video camera over your V1, you would see a mirror image of what's going on in the world. So that's V1. Unfortunately, most of the areas aren't as simple as that. That was actually relatively simple. So the first one that's different is V2. And so what happens in V2 is that V2 is kind of broken into two chunks. So it's kind of split apart like this. And so we have V2 plus over here, but V2 minus is kind of separated over here. And how does it get that way? One way of thinking of it is you start off with the visual field like this. Here's the horizontal line in the visual field. And there's the vertical line. And then I introduce some scissors. That's supposed to be scissors. And we just cut along the horizontal meridian. And so here we just cut it slightly. So there's the vertical line again. And now we've kind of snipped. We've done a little bit of a snip. And then we go completely crazy and stretch it completely out like that. And so then we end up with something that looks like this. I did a mirror image of it for the other hemisphere, but you get the idea, hopefully. So it doesn't hurt to flip it back and forth a couple times. Okay, so this is what actually V2 looks like. Strange. It's a strange area. That's the periphery right out there. So you can see that the upper field part is completely separated from the lower field part, except right at the center. Now, you might wonder, like, why go through that? Why do that? And one reason to do that is that allows you to kind of line up the borders. And so one of the problems you have is you've got this problem, you've got all these areas, and they all got to be pieced down onto the cortex. And if you're going to try to mostly line up their borders, you're going to run into trouble sooner or later. And so one way to sort of keep the borders lined up is to actually snip the areas into just a quadrant and then stretch that quadrant. And so this is a typical, many areas in the visual system look like area V2, where they've separated the lower field part from the upper field part. Now, what does this imply for how the map works? And so this is why I always have these simple map problems. And so let's take a simple map problem. Say, and you can do these map problems in two versions. You can say, here's what it looks like in the visual field, tell me what it looks like in the brain. But you could do it the other way around. Here's something in the brain, tell me what it looks like in the visual field. And I can work some of these problems during the review, so you can sort of get a feel for it. But let's just do the one. Let's have something in the visual field. So say we just put a line in the visual field. So this is our stimulus. So we just put a line in the visual field. So what does that look like? What does that look like in the brain? Simple enough problem. So how do you work these problems? Well, you kind of start someplace and then just go a small distance in one map, and then you just remember how this map is arranged and go a small distance, equivalent distance in this map. So we're starting at the middle. We're starting at the middle at the star, and let's just do the way this line looks like in V1. So where are we? We're in the upper field. We're in the plus. So we're in the plus near the star. So let's go to this map over here. And so where's the plus? Well, here's the plus down here near the star. So that means we're about there. So because we're going to start right here near the star. Now that's all well and good, but there's one critical thing to remember. That's near the star. And what's near the star, that's where the fovea is, where there's a very high density. And so that little line is going to be right over the highest density part of the retina. And when all those connections come out and spread out evenly into the lateral geniculate and then come up to V1, it's going to greatly expand that. And so that thin line is going to be really big because you're looking right at it with the fovea. So what is it going to look like? Well, it's going to be like a big fat line like that. Now, as you go away from the fovea, so as I head out on the line like this, I'm closer. You can see I'm closer to the horizontal meridian than I am to the vertical. So what's going to happen in the brain? It's going to be closer. It'll stay closer to that horizontal meridian than the vertical. So you'll get something that looks like. So that'll actually be what it looks like in the brain. So it'll have like a big fat line near the center of gaze, and then as you go out into the periphery, it'll get thinner and thinner. So that's all well and good. Everything's sort of like happy there. Now, what happens in V2? So in V2 we can say the same thing. So let's start in V2. So here's V2 upper. So that V2 upper is going to correspond to this plus quadrant, and V2 is going to get an expanded fovea. So there's going to be a really fat line right near the center of gaze in V2. And then it's going to stick closer to the horizontal meridian. So here's that fat line coming out and sticking closer to the horizontal meridian, something like that. And then it will sort of like go down, get thinner and thinner. So that's what a line would look like. That's what a line would look like in the cortex. So there's several things to keep in mind, like there's the upper and the lower field. You have to remember that anything that goes near the center gets really big. And then there's going to be multiple copies. So this is 2 copies of just this part of the line. So don't get confused. These 2 copies are two copies of this part of the line, not this part of the line. This part of the line is in the other hemisphere. Okay, so that was a very simple one. That's a very simple one. What if we cross the... So this was a simple one because we didn't cross the horizontal meridian. But if we cross the horizontal meridian, well, then more things are going to happen. And so let's take another example. What if we had like a big thing out here near the upper vertical meridian, and then we had a little tail coming out of it like this that went down. So this guy was stem number 1, and this guy is stem number 2. So let's plot out stem number 2 to see how this is working. So it looks like a sperm or something. So it's got a little tail coming out. So what would that look like in our map here? So let's start again. Let's just pick some place. So let's start, say, at this little head thing here. So this thing is, so where is that in the visual field? Well, it's in the upper field. It's in the upper field, and it's near the vertical meridian. It's near the vertical line, the vertical meridian. So let's go over to our map and say in V1. And so we're in the upper field, and we're near the vertical meridian. So here's the vertical meridian right there, running like that. But we're kind of far away from the center of gaze. And so that's going to turn into like a little bump, something like that. I'm going to move my V1 up here, V1 plus there. So it's going to be much smaller than it is in the visual field because this guy is way out in the periphery where the retinal density is much lower. Okay, so now what happens? Now we sort of trace along, heading toward the horizontal meridian. So we trace along, heading toward the horizontal meridian. Everything's going good until we hit the horizontal meridian. But now we cross over the horizontal meridian. And what happens in V1? Well, we just cross over the horizontal meridian. It's all good. So that's what this thing would look like in V1. It starts in the upper field. There's the upper field part near the vertical meridian. Here's the vertical meridian right there. And then it heads toward the horizontal meridian, and then it crosses the horizontal meridian into the lower field because now we're over this part of it is in the lower field. So what about V2? So what's going to happen in V2 is, I should have done this before, so there's V2 plus. Okay, so what's going to happen in V2 is there's going to be another copy of that little head thing there. It's going to be closer to the vertical meridian, so there's another copy of it right there. Okay, so that's all good. And now, what are we going to do? We're going to head toward the horizontal meridian. And so we'll head toward the horizontal meridian, so we'll cross our other line. So let's head toward the horizontal meridian. So we'll head toward the horizontal meridian, but now we sort of go off the edge. So now what? Well, because of this business, this is what V2 looks like. If you look at this map, so like here's 2 points, and in the original map they were close to each other. They were just above and below the horizontal meridian. How do they end up here? Well, they're snipped and stretched apart, and so they end up like something like that. So you can see those are 2 almost corresponding points like that. And so what does that imply here? Well, that implies that when we cross this horizontal meridian with our little tail there, that guy is going to now go all the way up here and then continue like that. So there'll be this discontinuity where as soon as you go a small distance in the visual field, and suddenly you jump to some other part of the cortex. So unfortunately, that's actually the way that everything you look at gets processed. And the example I always like to give is, let's just take a word. Like what? It's important to just sort of draw out the implications here. So say you look at the word, you're reading, and you look at the word stay. So we've got to divide stay, depending on where you fixate, into like 4 parts. So say we're fixating right there, just right in between the T and the A. That would be that might be a place you would fixate. You just, you're reading along, you just saccade, and you see the word stay, you fixate right there. So what does that imply? So what that implies is you're going to take the top of the A, and these 2 little pieces let's start with, before we do V2, let's just do V1. So what happens in V1? So V1 is relatively straightforward. V1 takes the AY, and since this is, the right visual field, that's going to go to the left hemisphere. So the AY is going to go into the left hemisphere, and then the ST, except for this part here, most of the ST is going to go into is in the left visual field, and that's going to go into the right hemisphere. Okay, so that's bad enough. So every word you look at gets split into 2 and sent to the left and the right hemisphere. That's very strange. You probably weren't thinking that that's the way reading works. So you have to put that together somewhere upstairs. But what about V2? V2 is going to be an even greater mess. So what V2 is going to do is let me just make another drawing. It's going to take just the bottom of the S and the bottom of the T and put that into one of the quadrants. So this is the lower quadrant, so it's going to end up sort of over here. So a little piece of the S and the T are going to end up over here, and then the rest of the S, and the rest of the T are going to end up in the upper part of V2, which is separated. And then the same thing is going to happen over here. So like the bottom of the A, like that, and then like the bottom piece of the Y is going to end up there, and then in another piece of V2, you'll have those things separated. So all the four quadrants are going to end up broken up into 4 pieces. And it turns out this is the case in many of the other visual areas that we'll talk about in just a minute. So it's a stranger world than you were thinking about how this visual information gets into the brain. So the brain is able to sort of deal with this and reassemble everything by making appropriate connections. But it's a pretty insane movie if you could actually see what was happening in your brain as you were looking over things. Okay, so any questions about visual map type problems? And you can always work them just by moving locally. Like start someplace, like we're near the center of gaze, or we're away from the center of gaze near the horizontal meridian, and then memorize where the map is in V1 and V2. And then once you've got that, then you can just move in small steps and sort of reconstruct the strange reality of the cortex. Yeah, question?
So essentially for V2, is all going to go in the same direction, just jumps, right?
It just jumps, yes. It just jumps. So essentially when any stimulus crosses the horizontal meridian, it's going to jump to the other quadrant. I mean, it could cross it from the other side too. If you're in the lower field, and you came up toward the horizontal line, then suddenly, right when you cross the horizontal line, it would jump down here. Okay, so now, in the last 10 minutes, all the other areas. And there's a lot of them. And the problem is, everybody agrees about V1 and V2. But as you go to higher areas, they're a little harder to find. And so there's more dispute. And so you end up with more names for the same area, unfortunately. We try to, in the field, we try to sort of keep the number of names down, but there's also, I discovered this area and I'm naming it. So there's a lot of disputes back and forth. I'm just revising a paper now with a bunch of aerial names in it and trying to navigate between all the different academics. Okay, so let's draw a nice big visual system here. Okay. Sort of a distorted brain, but good enough for our purposes. So let's put in just one of the major sulci. So here's the central sulcus. So we can sort of get an idea of where we are. Central sulcus there, okay. Okay, so how is this set up? So what we already did was the V1. So here's V1 lower field, V1 upper field. So here's V1. It just peaks slightly around. Let me label it in red so to make it a little clearer. So there's V1. Most of it's around the midline. So there's the horizontal meridian of that guy. So that was V1 minus because the world is upside down, and here's V1 plus. And then V2 comes out in front of that, and it has that split in its horizontal line. Comes around like that, and there's a lot of it that goes around the midline also. So that was so V2 plus and V2 minus. Okay, so you can see I've made them smaller to make room for all the rest of the areas. This is approximately the way they look like in real life. So the first next area is called V3, which, makes a certain amount of sense. We got V1, V2, V3. So here's V3. So that one is attached to the it's attached to the cut. So V2 was cut at the horizontal meridian, and V3 is only a quadrant. So it's only just the lower part of the world. It starts at the horizontal meridian and it goes back down to the bottom half of the vertical line. That's V3. But immediately there's naming disputes. And so there's another area right here in front of the upper part of V2 that is representing the upper visual field, but that one's called VP as opposed to V3. So you wonder, like, why call that? Isn't that just the other half of V3? This is an example of kind of disputes you end up with. But turns out, if you look in a macaque monkey at least, at V3 is very direction selective, very sensitive to the movement in different directions. If you go into area VP, which is representing a different part of the visual field, because V3 is representing the lower part of the visual field, and so VP is representing the upper part of the visual field. But if you look at VP, it turns out it doesn't care about direction. It cares more about color and shape. And so the actual sort of properties of the neurons in these areas are different. And so now you can sort of see what the problem is. You've got all these areas that are all got some kind of map of the visual world in them, but then all the neurons in there might have different properties. We have to try to decide, like, what to call all these different areas. And so things continue on. So then there's another area here. There's another horizontal meridian here. And another vertical meridian here. And so this area, that area there, it's called, it's got both upper and lower field in it. So this one is called V3A for V3 accessory, and here's V3A plus. So that's an area that is more like V1. It's got like an upper field and a lower field in it. Let me move my central just a little closer here. So as we move on, then what's kind of like the next best area? The next best area is an area called MT. And MT is sort of sitting in the superior temporal sulcus. So if we kind of open up our superior temporal sulcus like that, sort of like split it open, so we can sort of see down into it. We've got area MT in there. And what's the orientation of MT? So the orientation of MT is, it's got like the horizontal line is kind of vertical, and there's the center of gaze. And then it's got a lower field part that's behind and an upper field part that's in front. This is probably like the second best area compared to V1 and V2. Everybody agrees on this. There's only two names for it. So this guy is MT minus and MT plus. Okay, that's a nice area. Everybody agrees on that one. It's very. We'll talk about this area a lot. It's very sensitive to motions in different directions. It's a big processing stage of processing movement. If you read the human literature, they call MT the extrastriate body area. Is that a good name for it? Not in my opinion. MT is a better name. Obviously, if you move a body around, well, there's a lot of moving things, and you're going to get some activity in MT. It stands for middle temporal. So what's happened is, people have named all these things just with little abbreviations. After a while, they forget what the abbreviations stand for. So some people, they know the word MT, like what is the word MT? It's kind of like MT. That's how you pronounce it in phonetic alphabet, MT. It's a word. It doesn't matter what it means exactly. That's the way it sounds. You write it with an MT. So that's one of the problems that if you try to read any of these papers, you'll get completely buried in all the terminology for all these different areas. Okay, so let's continue on. There's another area right behind MT, and this is a small little area which has like irritatingly large number of different names. This one is called. Sometimes it's called. It's called the MT crescent, and other times people have called it V4 transitional, and then yet other people have called it the dorsal lateral anterior area. Okay, so you can see as you get into the weeds, you end up with a bunch of different names. But it's a small little area there. It's present in all primates. You can find it in the human, and you can find it in many other monkeys. Sort of looks like MT, very sensitive to movement. And then as we look forward here, there's another vertical meridian here with a couple areas kind of coming up. They might be related to these lower areas. There's a couple areas that sort of come up something like that. They have different confusing names. Sometimes they used to be called V4, so here we had V1, V2, V3, and then this general area used to be called V4, but now sometimes it's called LO for lateral occipital. So V4 or LO, and there's multiple areas there. And then if we continue marching forward, we get into an area called V7. Now, you might wonder, like, what happened to V6? And so it turns out that there's an area along the midline. So now we've got to draw along the midline like this. And so this is the corpus callosum right there. So if we look on the midline, there's a lot of V1 there. So here I'm going to draw V1 in. There's the periphery of V1, and so here's the lower field part of V1. It's supposed to join up there. And here's the upper field part of V1. So this is, V1 minus, V1 plus. And then there's, the rest of V2 is there. So here's the horizontal meridian of V2 coming along like that. And here it is, the rest of the upper part of V2. So this is V2 plus and V2 minus. So where's V6? Well, turns out there's a nice area sitting right. It's kind of sitting just past V3 called V6. And that area is very sensitive to large movements, like when the whole world moves. Like as you walk through the world, the whole world is moving. That area is very sensitive. It's got an upper and a lower field part. And there's another area in front of it called V6A for V6 accessory. That one's more involved in sort of reaching movements. And if you continue forward, there's an area, another visual area with a map, several maps in it called the precuneus cuneous visual areas. These are particularly involved with if you, like, these areas become active if you, for instance, imagine navigating through an environment. So if I close my eyes and just imagine like walking out the hallway, this area would become active. It will become active if you present some visual stimuli to it as well. But even if there's no visual stimuli, this area can become active. There's another area that's actually in front of V1, couple areas in front of V1. This area is called prostriata. And the origin of that term is kind of, it is something that looks like a primitive striate cortex. V1 is striate cortex. So sometimes this guy is just called area prostriata. And there's a couple areas, a couple additional areas, above and below that guy. I won't even label them. And if we continue even further forward along the cingulate sulcus, so here's the, this is the cingulate sulcus. There's another area sort of sitting up about here. So that's this, why did I do that? So this guy is the cingulate sulcus. That's along the midline. And so this one's called the dorsomedial, it's got several different names, but the dorsomedial frontal eye fields. So that's dorsomedial frontal eye fields. It's near supplementary motor cortex. And it's present in a monkey as well. We knew about this from a monkey. So sometimes it's called just cingulate visual area. You can see, or cingulate visual. That was when people didn't realize that it was actually the dorsomedial frontal eye fields. Okay, so now let's just continue back on the lateral surface. There's yet more, not too many more. We'll just leave a bunch of unnamed areas. There's caudal interparietal cortex, and eventually we get up to an area that there's multiple LIPs, but we'll call one of these guys like the LIP, and that's an area involved in it's particularly involved in attention and eye movements. And there's a couple of them, and they vary a little bit between people, but not so much that you can't see a general pattern across people. And if you continue further forward, you get up to an area called VIP. And I'm going to talk about both LIP and VIP in more detail. And there's multiple VIPs. There's probably like 2 or 3 of them, sort of something like that. Here, that's about the right number of areas. Now, this VIP is an area that has, this guy has visual plus somatosensory. So we've essentially reached the edge of visual cortex. And it turns out you have these visual maps that extend all the way up until you run into somatosensory cortex. And so where is somatosensory cortex? Well, somatosensory cortex, mato maps. So there's a bunch of somatosensory maps here which overlap VIP, because VIP has both visual and somatosensory. It's probably involved in things like when something's coming toward your face. If something's coming towards your face, you see it. It's in your upper field. You see it, and then it touches your actual forehead. It turns out that VIP has a map of the visual world superimposed on a map of your face. Not just your face. It turns out it goes down the body. It actually goes all the way down to the toes. It doesn't include the arms, but it includes the face and the neck and the shoulders and the chest and all the way down to the legs. And so this is a multi-sensory area. So it's a multi-sensory. And it's pretty much where you'd expect it, right at the boundary between visual and somatosensory cortex. And then finally, there's a series of areas that extend anterior to VP. So there's a little thin area here. We'll just put that one and not write a name in it. And if you look underneath here, this is where you have things like the fusiform face area. So, and that's an area that responds, as you might expect. It's got a map in it, an actual map in it. It's not just faces. It will respond to a car. So if you animators know that cars kind of look like people. There's the bumper, maybe a little bit of a nose. So if you just show a car to the fusiform face area, you'll get a response. Not as good as a face, but pretty good. So it's more than just the fusiform face area. It's obviously involved in all different kinds of object recognition. So we've got a whole series of we can call these inferotemporal areas. Inferotemporal. In a macaque monkey, these areas go all the way to the front of the temporal pole. They don't extend quite as far forward in humans. Now, last but not least, we've got some areas around MT. So there's a whole series of areas around MT, and we'll talk about a couple of them. And one of them is called MST. There's subparts to it, but we'll just call that guy MST. And there's another one that's got subparts also called FST. FST and MST. And then if you go even further forward, right here, there's an area that is sometimes it's called PIC, posterior vestibular cortex. And so this guy is, PIC, IC, or something like that guy's called 7B. And this guy has vestibular input. So one of the things, plus visual. So one of the things that happens is when you rotate your head, you've got some sensors that are telling you what direction your head is going in. And that information is being combined with the actual visual field, because obviously when you rotate your head, the visual field might rotate, and we need to sort of coordinate those. So if we continue forward into frontal cortex, there's a series of areas up here called the frontal eye fields. And those are kind of like the dorsomedial frontal eye fields, except they're the lateral frontal eye fields. Those are like the original frontal eye fields, so that's called FEF. There's another little area sort of tucked in here called PZ. This guy has some auditory and visual input. And then there's another two areas kind of sticking off like this, and we could divide these into dorsolateral prefrontal cortex, and we can call this guy PM, premotor ventral. So those guys have visual maps in them as well. And so what's the overall nightmare picture? Well, you can see the visual cortex is kind of like a squid attached around the back of the cortex. So there's a sort of like an area sticking out here into infratemporal cortex, and then there's another area kind of sticking out here that goes toward auditory cortex, And then there's another big area sort of sticking out here that heads towards somatosensory cortex. And then on the midline, there's an area kind of extending out into the precuneus. And then you can see another set of areas extending out in front of V1. So there's kind of like, like 1, 2, 3, 4, 5 streams coming forward in the cortex. And so that was a summary of about 30 years of research, too quickly, but just to give you some idea, there's a whole bunch of areas in there. You can find a lot of them by visual mapping. So that's one of the reasons for emphasizing visual mapping. One of the problems with finding them by, say, showing people pictures of faces is that there's so many things in the world. So, people tried faces, but they didn't try cars. And when they tried cars, they said, oh, cars work too. How about that? Animal faces work too. So one of the problems with more complex stimuli is there's so many of them. It's really hard to sort of decide. Whereas with visual mapping, it's more straightforward. We put something in this part of the visual field, see where the activity is. Put something in this part of the visual field, see where the activity is. And so visual mapping is a way to kind of rough out approximately where these areas are, a useful way of doing it. And you can use things like, if you're doing visual mapping and the place likes to look at faces, use faces. So you could put a bunch of faces over here and then move some faces over here and faces over here. So you can use more complicated stimuli. But the idea is that then we can sort of pick out the actual map and then compare that map across people. So that was not adequate, but it sort of gives you some idea of how much stuff is out there. There's this mosaic of about 40 plus 50 areas, little visual areas. Each of them are just like a centimeter or two across, and that's actually what's lying there under the cortex. How they work all together, when they're all turned on and they're all talking to each other, not well understood. Not well understood. But this is just to really sort of, make the point there's a lot of areas there, and there's a lot of areas interacting with each other there, and they're quite small. Okay, so that was going a little bit over, but any questions in the last negative 15 minutes, 20 minutes? Had enough visual areas for today? Yeah.
Are all these areas that you kind of just talked about part of the primary visual cortex, or are they separation and related? Because on the very first frame you drew, you showed that that cortex is pretty small relative to the entire frame. And this one kind of seems a lot bigger.
Yeah. No. This is well beyond. So the question was, is this primary visual cortex? No, it's well beyond primary visual cortex. So the official primary visual cortex is just V1. Yeah, it's just V1. And so, V2 is sometimes called secondary visual cortex, and then they just went completely haywire once they realized how many additional areas there were. So, yeah, so this is well beyond. These are all secondary, tertiary, higher level visual areas. I think the thing that's new is that people just didn't realize that these maps just continued all the way until you ran into somatosensory cortex. You didn't somehow end up with just some higher level area. You just ended up like at VIP with a visual map on top of a face, or sort of like an upper body map. And so the whole sort of map idea continued a lot further into the system than people were initially expecting. Now, this doesn't mean that they're not higher level. They are higher level. They're doing all different kinds of higher level things. It's just we use the maps to try to figure out where the parts are.